There is often a need for a solution of a known concentration when we are doing chemistry experiments in the lab. Producing such a solution accurately takes some skill and not a little thought. To demonstrate the process, I'm going to assume that I need a solution that has a concentration of 1/1000th of a mole per litre. However, I only need 100 millilitres of this solution. The compound that I'm going to use is called potassium ferricyanide. The first thing that we need to do is to calculate how much of the solid we will need to weigh out. So here's the formula for the compound, along with its molecular mass. Hence, 1 molecular mass gram equivalent, 1 mole, will have a mass of exactly the same numbers, but in grams. If you need a refresher on the definition of the mole, I'll put a link in the description below. Our target concentration is 1/1000th of a mole per litre. So we calculate the mass of 1/1000th of a mole. Since the units of concentration are moles per litre, we need to convert the volume of the solution, which is 100 millilitres, to litres. We do this by dividing the volume in millilitres by the number of millilitres in a litre, which is 1000. This shows that our solution is only 1/10 of a litre, so we only need 1/10 of the mass we calculated in the previous step. Now at this point, we hit a problem. The mass we need to weigh out is rather small. A normal analytical balance weighs to 4 decimal places of a gram, which in our case means we will only be able to record 3 significant figures. This is okay for some experiments, but I want to work much more accurately than this. To do this, I'm going to make up a solution that is 10 times more concentrated than I need, and then dilute some of it to the required concentration. So let's amend our calculations. My target concentration is now 1/100th of a mole per litre, so we work out the mass of 1/100th of a mole. The last step is to allow for the volume of the solution as before. Now we know the mass required, we can go to the lab. So here we are in the lab with the necessary equipment. Our first job is to weigh out the required quantity of compound. To weigh out exactly to the nearest 10,000th of a gram will be extremely time consuming and near impossible. To get around this, we'll use a phrase that can be confusing when you first see or hear it. It is weigh out accurately, approximately. The key here is the comma between the two words. If you read out the phrase, putting a pause where the comma is, it becomes clearer. Weigh out accurately. Approximately 0.3293 grams. The important point here is that we need to know the concentration accurately, not that the concentration happens to be a round number. The calculations before we got to the lab give us a mass to aim for, to get the concentration at the right level. We'll use the actual mass to calculate the final concentration. Now, most A-level texts describe the use of a weighing bottle. Whilst this can be useful for compounds that absorb moisture from the air, most of the time at university we use one of these. This is a weighing boat. It's made of lightweight plastic and is designed to avoid having corners that a solid could get trapped in. It's also very smooth and water repellent to help ensure the full amount of the solid is washed into the solution. So I should point out that our analytical balances are on a stone plinth to minimize errors due to vibrations, and that they have windshields around them to avoid drafts changing the reading. They are also regularly calibrated against known standards to ensure accuracy. So let's weigh out accurately approximately the mass we calculated. We calculated that we need 0.3293 grams. I've ended up weighing out 0.3247 grams, so we record this in the lab notebook. The solid is now transferred to a beaker. The weighing boat is rinsed out with deionized water to make sure all of the solid weighed out is transferred. Since this solution is going to have a final volume of 100 ml, we can use about half of that volume to dissolve the solid. The exact volume we use here is not important. A glass rod is used to stir the solution until the solid is completely dissolved. Once dissolved, the solution is transferred to the volumetric flask. Again, it is important that all of the solution goes into the flask, so more deionized water is used to rinse anything that has come into contact with the solution, and the rinsing's transferred to the volumetric. The next step is very important. We have taken great pains to ensure that we know the mass of the solid used and that all of it has made it to the volumetric flask. However, concentration is made up of two terms: the number of moles of the solid dissolved and the final volume of the solution. It is therefore vital that we make up the solution to the correct volume accurately. The volumetric flask is made with a narrow neck so that small additions of liquid result in relatively large changes in the level within the flask. This volumetric is designed to measure 100 millilitres accurately, so the line on the neck is at this volume. Hence, we need to add water to the flask until the level, in particular the bottom of the meniscus, is on the line. I'm using a transfer pipette to add water dropwise until the level is exactly on the line. Once at the correct level, it is quite likely at this point that the concentration at the bottom of the flask is different to that at the top. So we stop at the flask and mix by inverting it a few times. We've now made our solution. But because we weighed out approximately the right mass, we don't know the concentration of the solution to any precision. To find this out, we do a very similar calculation as before, but use the actual mass of solid used to create the solution. We want to know the concentration of the solution in moles per litre, so we need both the number of moles of the solid and the volume of the solution in litres. We know the mass of the solid used, so we divide this by the mass of 1 mole to calculate the number of moles of the compound used. The volume of the volumetric flask is 100 millilitres, so we convert that to litres by dividing by the number of millilitres in a litre, which is 1000. Now we can calculate the concentration of the solution by dividing the number of moles by the volume in litres to yield a concentration in moles per litre. Since we know the mass to 4 significant figures, we can quote our concentration to 4 significant figures too. So now we have a solution of an accurately known concentration. However, for the experiment I want to perform in the lab, I need a solution that is 1/10 the concentration of the solution I've just prepared. So all I have to do is take a sample of the solution I've just made and dilute it to 10 times that volume. I'm going to take 10 millilitres of this solution and dilute it to 100 millilitres. To do this accurately, I need to use accurate glassware, so the 10 ml of solution will be measured using a pipette. This is then placed in a 100 ml volumetric. Made up to the mark. And mixed. At this point, we can label our solution with the correct concentration to 4 significant figures.